Hi, my name is Krishna Maran and this is Physics 2212 Lab 4. So for this lab, the main principles that we used were that the node rule is current in equals current out, and then the principle of energy conservation, which is the loop rule, saying that the potential difference across the whole circuit will be equal to the potential difference of each separate part all added together. And then V equals IR, which is the current times the resistance, and then V is also equal to Q over C, the charge over the capacitance. So during this lab, we predicted the behaviors of circuits in series and parallel for resistors and capacitors, and we used multimeters and ammeters to measure the values of current and the potential differences in various parts of the circuit. The first circuit we made had two batteries of 1.5 volts, as you can see in the image, and we wanted to have a predicted current before we made this, and the predicted current I got was 0.02 amps because you do 3 volts over the total resistance, which is 147. Here are the three circuits that we made for part 1 of the lab. On the top is the first one we made, as I described in the last slide. In the bottom right is the second one, which is the exact same thing, but on the top part we put a voltmeter to connect the two wires instead, which is why the current is 0 amps, because the voltmeter does not carry current, so it is not a complete circuit. And then in the bottom left is the third one, which is the same as the top one, except we included a parallel ammeter parallel to the resistor on the bottom right part of the circuit. For the potential differences across the circuit, it would only change between C and D, where it would be 0.959 volts, and E and F, where it would be 2.041 volts, and A and B, it would be -3 volts, because that is a whole circuit. Other than that, it all stays the same. So as you can see on the graph to the right, it starts at 3 volts at location C, and then it will go down roughly 1 volt after the 47 ohm resistor, and then stay, and then after the 100 ohm resistor it would go down to 0 and stay at 0. Now for the calculations. Resistance is equal to the voltage over the current, so the resistance of the 47 ohm resistor calculated would be 0.96 over 0.02, which is equal to 48, and then the resistance of the 100 ohm resistor would be 2.041 divided by 0.02, which is equal to 100 ohms. And then the resistance of the wire would be 0 divided by 0.02, which is 0, and the resistance of the ammeter would be 0 over 0.02 again, which is also 0 ohms. Part 2 was the RC circuit. So the battery was 9 volts and the capacitor was 0.2 farads, and then we used 10 ohm and 20 ohm light bulbs. So after we turned on this circuit, the light bulb turned on and then slowly dimmed over a period of time. So the charging times for the capacitor for the 10 ohm light bulb was 7.63 seconds, and the 20 ohm light bulb was 17.48 seconds. The discharging times of the capacitor for the 10 ohm light bulb was 11.57 seconds, and the 20 ohm light bulb was 20.19 seconds. Now, the formulas for part 2 is the conservation of energy, which can be split up into the potential difference of the capacitor plus the potential difference of the resistor is equal to 0. And then it can also be said as that Q over C minus IR is equal to 0, which is the potential difference of the capacitor equals the charge over the capacitance minus the current times the resistance equals 0. And this can once again be split up into the charge over the resistance times the capacitance plus the derivative of the charge over time is equal to 0. So as you can see, we made a chart of ln of the voltage over the initial voltage versus time. So the slope of this would be -1 over the resistance times the capacitance, and the y-intercept would be ln of the initial voltage, which would be 0, which is why it starts at 0, and then there's a negative slope. Now for the discussion questions. What if we were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? So the ideal ammeter would have 0 resistance, while a real one will have some resistance. So the current will shown to be less in the model. Next, what if we were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? And would this prediction happen in real life? So in an ideal situation, the capacitor would be charged instantly without any wait, but in real life, the capacitor only reaches full charge over time, so it'll take more time.